day students. Today we are going to discuss about matrix methods in ray optics. In ray optics or geometrical optics, light is considered as a ray or a straight line. This is because the wavelength of the light taken into consideration is very small or very insignificant compared to the size of the object with which light is interacting. The dimension of light is just, the wavelength of light is just in nanometers. But the surface upon which the light reflects or refracts, or the distance through which light translates, is observed in our dimension, that is in centimeters or meters. So it is the scale is very large compared to the wavelength of light. Hence, in this case, we can consider the ray or the straight line nature of light. Now, when light travels such, it may come across different sets of medium. Like when light travels through a crystal, as shown in the first figure. This is the first figure. You can see that as long as light is traveling through air, initially, it travels in a straight line. Then it comes across the first surface of the crystal where it bends or refracts. After it has entered the crystal, it will travel in a straight line through the crystal because the crystal is a homogeneous medium. Now, upon the second surface of the crystal, when light reaches that point, at the surface it again refracts. Hence, if light is traveling through different sets of medium as shown in the second figure, it will undergo a number of translations and refractions. So the basic operations that light undergo is translation and refraction. Here in the third figure shown, you can see the basic components of a microscope. So in a microscope, we have a number of lenses. It may be double convex lens. There may be slits. There may be plano convex lens and all. See, you can see a number of lenses in the figure. So if we try to calculate what is the position of the image, or what is the size of the image, what is the nature of the image using lens convection, it will take a lot of time. Like from the initial point of the lamp filament, if this is my object plane, then from the lens I need to find the image plane using lens convection. Then again, using this as the object plane, I need to find the image plane of this lens. Okay, and then again, using this as the object plane, I need to find the image plane of this lens. And then again and again, it repeats on for if there are a number of lenses. So this process becomes very tough in calculating. In order to reduce this complexity, it was K. Hallback who introduced the matrix method in ray optics. Okay, so according to him, light ray in the object plane can be represented by a matrix X, Y, Z. Okay, and the light ray in the image plane can be represented by a matrix X prime, Y prime, Z prime, the image plane. Okay. Now, these two matrices will have a relation, and since light is considered paraxial or as straight lines, it will have a one-to-one correspondence. That is, the X coordinate in the object plane will be related to the x prime coordinate in the image plane. Likewise, y coordinate will be corresponded to the y prime coordinate in image plane, and the z coordinate in the object plane will be corresponded to the z prime coordinate in the image plane. So all the coordinates will have a one-to-one correspondence. And if in the light in the object plane undergoes a number of translations or refractions, all of that can be simplified into a simple matrix which acts upon the object plane to give the image plane. First, see what are the basic operations that light undergo. Here, in this figure, you can see that light is falling upon a double convex lens and it refracts through it. So here, when light travels from point A to B, it undergoes translation. Now at point B, that is the surface of the double convex lens, it undergoes refraction, right? Now from B to C, light is traveling through the lens of a constant refractive index. If it's a glassless lens, the refractive index will be around 1.5. Okay, so it is a homogeneous medium. Again, their light will undergo translation. Okay, fine. Now at point C, again it is the surface of the double convex lens. Light undergoes refraction. Now from C to D, where D is the focus of the lens and D is the image plane, light undergoes translation. Right. So for a simple lens, we need to consider a lot of operations undergone by the light ray. Okay. All these operations can be simplified, okay, can be taken together and be represented by a common system matrix to represent the lens. Okay. So any uh, optical component can be simplified into a system matrix, or any path taken by the light ray can be simplified into a system matrix using matrices. Okay. Now let us first learn how to represent a ray in matrix methods. A ray is specified by its distance from the axis and its angle made with the axis. So we have taken into consideration coordinate system where this axis is the z-axis. Z-axis is usually taken as the optical axis with cylindrical symmetry. Okay, and this axis is considered as the x-axis. In order to represent a ray, we need to define its distance from the z-axis and the angle made with the z-axis. Let us assume a light ray from point A to B. Its distance from z-axis is represented by x and the angle made with respect to the z-axis is represented by alpha. The angle made with respect to x-axis is also denoted by an angle theta. Here, the ray coordinates at A is represented as x1 alpha 1, and the ray coordinates at B can be represented as x2 alpha 2. We can also define another parameter, optical direction cosine, given as lambda is equal to mu refractive index of the medium into cos theta. Hence, the ray coordinates at A can also be defined as lambda 1 x1, and the ray coordinates at B can again be defined as lambda 2 x2. In matrix method, we usually don't take the coordinate representation. We take the matrix representation. Hence, the ray matrix at A can be represented as matrix lambda 1 x1, and the ray matrix at B can be represented as lambda 2 x2. Now, let us derive the matrix used to represent the translation of a light ray from one point to another. So in this figure, let us assume that light is traveling in a homogeneous medium from point A to B. Since the medium is homogeneous, light will travel in a straight line path. Here, the distance of point A from the z-axis is represented as x1, and distance of B from the z-axis is represented as x2. If I draw a line parallel to the z-axis with point A and point B, extrapolating this line, I can define the angles. Let this be angle alpha 1 and this be angle alpha 2. I'm going to denote this point as C. This point is A prime and this point is B prime. Okay. So at A, the incident ray can be represented as x1 alpha 1, and its direction cosine lambda 1 can be written as mu 1 alpha 1, where mu 1 is the refractive index of this medium. At B, the image ray can be represented as x2 alpha 2, and the direction cosine lambda 2 is given as mu 2 alpha 2. Now, according to this figure, we can see that the light is traveling through a homogeneous medium. Hence, mu 1 will be equal to mu 2. Now, the angle alpha 1 is also identical to alpha 2. Hence, direction cosine lambda 2 can be written as mu 1 alpha 1. Okay. Now, x2 can be written as x1 plus bc, right? From the figure, you can see that. This can be written as x1 plus. I'm going to substitute for BC. If I take the tan of alpha 1, I can write BC is equal to, let me write it here, tan alpha 1 is equal to opposite side BC divided by adjacent side AC. I'm going to define the distance traveled as capital D. The distance traveled by light ray in the z-axis as capital D. Hence, AC becomes D. So BC can be substituted as D times tan alpha 1. Well, when considering paraxial rays, the value of alpha 1 will be very, very small. In that case, tan alpha 1 can be approximated as alpha 1. Hence, this expression becomes x1 plus d alpha 1. This is because since the value of alpha is very small, tan alpha becomes approximately equal to alpha. Now the direction cosines lambda is equal to lambda 2, written as mu1 alpha 1. So I can get an expression for alpha 1 as lambda 1 by mu 1. This implies x2 is equal to x1 plus d lambda 1 by mu 1. Okay. Now further into the equation, I'm going to just rewrite it as x2 is equal to 1 into x1 plus d by mu into lambda 1. Okay. And lambda 2 is equal to 1 into lambda 1 plus 0 times x1. Okay, fine. So I have two sets of equations. Let this be equation 1 and this be equation 2. I can use these two equations in the matrix form as lambda 2 x2 is equal to some matrix into lambda 1 x1. Okay, so this matrix that I have written, I'm going to find the values here. From lambda 2, I have 1 into lambda 1 plus 0 into x1. And x2 is equal to 1 in, d by mu into lambda 1. D by mu into lambda 1 and 1 into x1. Okay, so this is your matrix to represent the translation of light ray from point A to B. Okay, so we see that the translation matrix is a 2 by 2 matrix. Okay, and usually the property of the translation matrix is that determinant of the translation matrix will be equal to 1. Thus, the translation matrix is represented as matrix T is equal to 1, 0, d by mu 1, where d is the distance translated by the light ray in a homogeneous medium of refractive index mu.